Greetings. Before we move on to the topic of differentiation, let's explore limits and continuity. If you look at the top left, that's what a limit looks like. What you do is you take the values and approach it to a constant so that the output of the function will tend towards a defined value. And you want to see how a limit that exists, you look at the picture on the right. Now, for continuity to exist on the graph, make sure that the graph is a continuous function. There must be no gaps or sharp corners like cusp. There must be non-removable factors, means the numerator and denominator cannot have two factors that cancel each other. And there must be no asymptotes for which the value is undefined there. Now we are into the topic of differentiation, and to do this we will have to look into the first derivative. So the first derivative will give you a gradient function of a tangent. Using limits, you can observe that 2 points along the line will merge into a single point, and this will give a tangent line. Derivative you can see in differential expressions. Many can be found using first principles, and some of them they can be found when the inverse is changed to the original function and then you do substitution. For rules, there are 5 of them. You have add and subtract, chain rule, product, quotient, and logarithmic, and all of these can be found by finding the proof on the internet. The fundamental idea for differentiation is that when the derivative is 0, there's a stationary point, since the gradient is 0, just a horizontal line. And the fundamental, like I said, on the graph, differentiation is used to check for rate of change of y with respect to x. After you've mastered the first derivative, now we look at the second derivative. So to do second derivative is the same as the first, just that the second derivative is the rate of change of the first derivative, like rate of change of the gradient function. So you can see the second derivative is used to test the type of turning points. So just make sure that the gradient function is 0. Then you need to find all the stationary points from there onwards. And if you found that the second derivative is like less than 0, then it's a maximum point. If second derivative more than 0, then it's a minimum point. If it is 0, then you get an inflection point. And for fundamental purposes, it's a rate of change of gradient with respect to x. Now let's look at parametric differentiation. It's used when both x and y are functions of t. Other variables can be used. X and y are differentiated separately with respect to t. This can be used for rate of change in real life applications such as expansion, where area and volume are functions of length. If you look at the picture on the right, you can see how parametric differentiation is conducted. And if you want to find dy dx, you need to do the chain rule, and that's how you do first derivative for parametric. If you look at the second derivative for parametric, eventually you should realize that in order to differentiate with respect to t, you need to use the chain rule and make sure you use the differentiation technique we're going to use. Now let's explore implicit differentiation. It is used to differentiate an equation where separating terms is difficult or impossible. It uses a combination of both chain and product rule. For it to work, one variable must be a function of another variable. In the common case where y is a function of x, just to make sure when you conduct implicit differentiation, there must be no quotients. Look at the picture at the bottom. You can see how you differentiate y using the chain rule. And if you differentiate using this, if you look at this example, you can see how the product rule and chain rule works. And just make sure that you take note of the sign. And by accounting all that, implicit differentiation is possible. Now we're looking into logarithmic differentiation. Well, logarithmic differentiation is not exactly like a type of differentiation, but rather it's like a bypass technique where it simplifies complex products, quotients, and exponents for easier differentiation. It uses log laws, and separation can often overcomes the laborious processes. This will reduce a lot of working space compared to other methods. And if you look at the bottom left, that is how you perform logarithmic differentiation. You just like use lot of laws, separate the terms, and then eventually you get your simplified differentiation. If you look on the right, this one is very interesting, where this kind of differentiation where you get a quotient, it will be very useful when you do integration later. I think that is all for this video. I hope to see you in the integration video. Thank you.